And the next presentation will be given by Professor Gerard Heuveling. Professor Heuveling is a senior researcher at the International Soil Reference and Information Center and a special professor in pedometrics and digital soil mapping with the Soil Geography and Landscape Group of Wegeniнгену University in the Netherlands. He built his scientific career in the field of spatial uncertainty analysis with application in the soil domain as a main focus. He has been awarded several times for his outstanding achievements in research. Professor Heuveling will present a lecture named Spatial Interpolation for Mapping the Environment.
Thank you, Mr. Chairman, for a very kind introduction. It's my pleasure to be here. I would really like to thank the organizing committee for inviting me to present at this conference. It's an honor. I'm honored to be here, and I'm also really very happy that I can be here physically, because it's really a beautiful location here, and it's great to be in Belgrade. I would also like to congratulate the faculty, all staff, with their 175th anniversary. As you can see, I'm from the Wageningen University from the Netherlands, and I think many of you will not know of that university, because that university does not have a department or a faculty of civil engineering. It's actually a university mostly on agriculture, life sciences, and food sciences, and actually it is a world-leading university in those domains, but we do not have anything really related to civil engineering. That university that I'm with is also, 2 years ago we had the 100th anniversary celebration. So we are still much behind you, and of course we will never catch up with you in that sense, but we have to wait some time before we can actually celebrate our 175th university. It's also very nice to be here because I can now taste some, get a flavor of other disciplines. Like the first presenter, I did not know anything about concrete, and it was really nice to see such a nice overview of the history and the development, and see those beautiful pictures of buildings and bridges made by concrete. And then I thought about the famous book of the Nobel Prize winning author on the bridge over the Drina. I got it from one of the colleagues here in the room a few years ago, and I read it, and I guess that bridge is not made from concrete, but it is a strong bridge and already holding like so many hundreds of years. Okay, so my talk will be about spatial interpolation. And when I was invited, it did not take me long to come up with this topic, because the Department of Geodesy and Geoinformatics of the Faculty of Civil Engineering of University of Belgrade has done quite a lot of work on spatial interpolation, and I myself too. So I thought that this would make really a worthwhile topic to give you a bit of a historic overview of spatial interpolation for mapping the environment. So what I will do, I will just go briefly through the history of that. I'll start off with simple deterministic spatial interpolation methods that are from the first years of geoinformation science, at the time when the GIS, the Geographic Information Systems, were developed. So I'm talking about the 1970s now. And then I will go through time and for example, talk a little bit about geostatistics for mapping, about machine learning, and I will also, during my talk, I will emphasize the contributions from the geoinformatics group of the University of Belgrade. So let's maybe first explore a bit what is actually spatial interpolation, and maybe the easiest, the nicest way of doing that is to give some motivating examples. So here you see just an example of a map from the northeast of the United States, and every circle here is an air quality monitoring station. So we can measure the air quality at points, but what we want is actually, we want to have a map of the air quality. This is another example from soil science. I work mostly in soil science. So here, in a catchment, there's plenty of locations where the soil moisture and other soil physical, soil chemical, and soil biological properties can be measured, but it is always measured. You take a soil sample, or maybe you have an instrument installed in the soil. You only measure at points, but what we want is a map. And here maybe a third example is more from meteorology or climatology. This is the north or the center of England. Every plus in this graph is a location where a rain gauge is installed. So it's like a meteorological station, and they measure the rainfall, they measure the precipitation. But you really would like to have a map of the precipitation. And maybe you also noticed that in this area there are 3 locations where there is a radar. And we know, of course, that radar can actually measure the rainfall spatially, exhaustively, but those measurements, those radar images, they have some uncertainty, and you might want to include that information when you do the mapping, the interpolation from the point observations, and we will be talking about that later as well, how you can, the techniques that have been developed in geostatistics and machine learning to deal with that kind of information too. And I think you can also come up with examples from civil engineering where there might be a need for spatial interpolation. Actually, before the conference began this morning, we had a coffee downstairs and we were talking about earthquakes and the design of buildings to be stable enough to survive earthquakes. And well, then you probably need a map of the earthquake densities. And then you have point measurements where the earthquakes occurs. And I do know that in spatial statistics, they are dealing with these kind of issues, trying to make maps of the earthquake incidence, the frequency of occurrence, and maybe also about the magnitude of that from those point observations. So these are just a few illustrating examples, but you, within your domain, I'm sure you can think about cases where you would like to do a spatial interpolation. So what we want to do is actually very simple. We have at a finite number of locations within our study area, we have measurements of our variable of interest, and we like to interpolate, we like to predict the value at a measurement, at a location where we have no measurement. And in this graph, this is illustrated, so the blue circles are the points where we have a measurement, and the red one is where we want to predict. And well, the graph also already tells us a little bit how do we do that. Basically, we use the measurements to make that prediction, and we mainly rely on the nearby measurements. Why do we do that? Well, that's actually also what those deterministic spatial interpolation methods do. They are inspired by the first law of geography. So Tobler's first law of geography says that everything is related to everything else, but near things are more related than distant things. I really like this law, the formulation of the concept of basically you might call spatial correlation. So given this law, when you need to make a map and you want to interpolate, you probably pay more attention, more confidence, you give bigger weights to measurements nearby than measurements far away for spatial interpolation, and that's simply because of this first law of geography. So this is the early years of GI science. Those deterministic and really very simple methods of spatial interpolation were developed. I put a few here: nearest neighbor interpolation, inverse distance weighted interpolation, splines, trend surfaces, and there's many more techniques like radial basis functions, and maybe also have heard about TINs, T-I-N, triangular irregular networks. So there's various deterministic interpolation techniques that are used, and I'm just going to illustrate that for a very simple example of, we have here 8 measurements. The yellow is the high values, and the dark purple is the low values. So when we interpolate these, just a simple example, and we would use nearest neighbor interpolation. Basically, the idea is that your prediction at any location in your study area is equal to the nearest observation. And then your map becomes, well, gets this kind of a shape where you get polygons, and these are called Dirichlet polygons or Voronoi polygons. So you get really sharp boundaries between the areas where you cross the border basically from the nearest observation. So all credit, all weight is given to the nearest observation when you do a prediction. Inverse distance weighted interpolation takes a bit of a different approach. Every observation gets a weight in your interpolation, but observations nearby get a higher weight, but it's not like a binary 0-1 case like you have in inverse distance interpolation. both those two types of interpolation techniques, yeah, they make basically use of this equation, right? So the prediction z hat, so z is our target variable, x is a location, so x0 is our prediction location, the location where we do not have a measurement, and all the xi's from I equal 1 to n are the measurement locations. So basically, our prediction z hat at x0 is some kind of a linear combination of the measurements, and the lambdas here are the weights. So in nearest neighbor, there's all the lambdas are 0 except for 1, which is 1, and in inverse distance interpolation, the lambdas are, well, inversely related to the distance to the prediction location. It's all really simple from the early days of geoinformation science. So there's many of those techniques, and then you ask yourself, which one is best and which one should I use? Even if you use inverse distance weighted interpolation, you have to choose what they call the power. So is it inversely proportional to the distance, or is it inversely proportional to the square of the distance? You really don't know what's best. So in order to decide that, you need some kind of a statistical model of spatial variation. And that is what was developed in geostatistics. And geostatistics has its roots in mining, in geology. It was developed mostly in South Africa, where they were dealing with a problem that they drill for ore, and they like to interpolate in between those drilling locations. Also in France, it was strong at the Centre de Géostatistique in Fontainebleau near Paris. And the idea of geostatistical interpolation is that you don't really look at the distance, but actually you look at the degree of spatial correlation. And of course, because of the first law of geography, distance influences the spatial correlation, but it's maybe not a linear correlation. It's a bit more complicated than that. And that is what we, and if you're not familiar with that, I'm not going into the details at all, of course, but we need this semi-variogram which characterizes the degree of spatial correlation as a function of the distance. And you basically pose a geostatistical model of the reality, and given that statistical model, that geostatistical model, you can actually optimize the weights that you use in your spatial interpolation. And you choose those weights in such a way that the expected squared prediction error is as small as possible. That's the principle of geostatistics. And geostatistical interpolation is also known as kriging, and it's named after Danny Krige, who was a mining engineer from South Africa. So he developed that technique, I think, well, somewhere in the 1960s perhaps, but it's really since the 1980s that geostatistics has become more widespread and very often used in all of the earth and environmental sciences. And there's many different types of kriging. There's co-kriging, block kriging, disjunctive kriging, but I just want to mention two of them, ordinary kriging and regression kriging. And ordinary kriging is the most basic form of geostatistical interpolation. And it just uses the measurements to interpolate, and it optimizes those weights, those lambdas that I showed you before. It was used a lot in the past, also, for example, for soil pollution mapping, but nowadays it's not used that much anymore. It's being replaced by more advanced geostatistical techniques, and perhaps regression kriging is the best example of that. The difference between ordinary and regression kriging is that in regression kriging, you not only rely only on the measurements that you have at your measurement locations, but you also use external explanatory variables. So you model some kind of a trend, a geographic trend, based on explanatory variables. And I'll give you an example in a minute to illustrate that. Well, that example is here at the bottom, the spatial interpolation of the soil pollution, so the arsenic concentration of the soil near a copper smelter. It can probably benefit from information about how far is my prediction location from the copper smelter. And maybe also take into account the prevailing wind direction and the topography of the area. And here is my first example of the work done by the geoinformatics and the geodesy department within the Faculty of Civil Engineering of Belgrade University, where they applied this regression kriging technique to map the arsenic concentration. The study area is in Bor, so in Serbia, and I think it's the biggest copper mining area in Serbia. And so you do have a problem with the soil pollution in the nearby environment, as you can see in this map, because every dot here, every red circle is, and there's also blue circles, maybe you notice them here, so there are lower concentrations of arsenic. So every location is a measurement where is a location where a soil sample was taken, and then we would like to have a map. In regression kriging, you not only interpolate using the observations, but you also make use of that external explanatory variables. In this case, well, the distance to the copper smelter, but not the distance itself, but it's really corrected for wind speed and also for topography. If your slope, if the hill is facing the copper smelter, then you probably get more deposition of arsenic than when it's opposite to. So that was all included, and then this is the final resulting regression kriging map of the arsenic concentration for a certain depth of the soil. An example of regression kriging. Another example of regression kriging, also from the geoinformatics group, is the extension from spatial interpolation to space-time interpolation. So here a global mapping was made, so for the whole world, of the daily temperatures for a whole year. So every day of the year was interpolated both spatially and in time. That was a really nice example of regression kriging, extending it from spatial to space-time. And I will show you just one of the results of that. This is for the USA, but it was done for the whole world, for the USA, and only 4 days in the year, the first 4 days of the year, but basically with this space-time regression kriging, maps were made of the daily precipitation for the whole world. And you can see the change over time as well as the variation in space. So that is really what I wanted to say about geostatistics. I could say much more about that, but let's move on to machine learning. Artificial intelligence, or perhaps statistical learning, whatever we want to call it. This is really more recent, I think maybe from the start of this century, so maybe 20 years ago it started off a little bit, and we're now applying it quite a lot for spatial interpolation. So the idea of machine learning is if you have a large data set, big data, you can establish relationships between the variable that you want to know, the dependent variable, the one that you want to interpolate, and all those explanatory variables, like a little bit like in regression kriging. So you fit some kind of a statistical model, a regression model, or maybe a classification model if your dependent variable is a categorical variable like soil type or land use, or you fit that statistical model and then you apply that statistical model to predict. Now, technically speaking, you may discuss whether machine learning actually does spatial interpolation, because it does not really interpolate in between points. Well, it does make a map, but it just fits some kind of a statistical model that says this is the relationship between the dependent and the explanatory variables, and then it applies that. And there's many techniques for doing machine learning, like random forest, gradient boosting, artificial neural networks, and so on. And I'm not going to explain those to you. I'm also not like the real expert on that topic. So when we apply those techniques, the difference with regression kriging that I mentioned before is that we have much more flexible models to fit that trend. They are non-linear, they are very advanced, very clever techniques to get all of the information out of those explanatory variables. And we can also easily use 100 or 200 explanatory variables and capture from all those variables the information that it contains about your dependent variable. I myself, I think I mentioned that already, I work a lot in soil mapping, digital soil mapping. I work in soil science. And here is the flow chart that we use yeah, the mouse is here, for digital soil mapping using machine learning. And it's just a bit of a repetition what I said in words, but it might be interesting, worthwhile to also go through this flow chart briefly. So basically what you have soil observations from the National Soil Institute. They have a database with all the soil data. You have your often remote sensing based maps of explanatory variables. We also call them covariates in digital soil mapping, in machine learning. And they are maps like, for example, the vegetation index, the elevation, the slope, the precipitation, and so on. And if our goal would be to map precipitation in England, like I gave in the first example, we probably would be using our radar map over here as an explanatory variable. And then you do what they call the GIS overlay. You simply check what are the environmental variables, the explanatory variables at all those measurement locations over here. And then you get a regression matrix. So y is the dependent variable, the variable that we want to know, and all those x's in this notation, now they are the explanatory variables. We fit a model, we train, as they say, we calibrate a machine learning model, and then we apply simply that model to make our map. That's basically the idea. And we sometimes also want to check how well did we do, and we would use a cross-validation approach for that. I'm not going to explain how that works. Here is an example of that. Soil grids. Well, I think the chairman also introduced me and said that I not only work for Wegeniнгenu University, but I also work for ISRIC World Soil Information. It's an institute also based in Wageningen. And well, our mandate, our mission is to share the world for free with soil information. So, for example, we have the Soil Grids product, which is a 250-meter resolution map of the soil properties for the whole world. And yeah, the Belgrade geoinformatics group really made very important contributions to the development of soil grids. Here is a map of the soil pH for the globe at a certain, we make it at multiple depths. So you can, if you're interested, I'm not sure, you could visit soilgrids.org website, and there you can download all those maps for free. But I did mention that, you know, random forest or machine learning, basically, we can ask, is it really doing spatial interpolation? Because it's not really using the data and the distance, etc. It's just fitting a statistical regression kind of model. And it should, in principle, be possible to do better than that. To also make use of the fact, how far away are the measurements for my prediction location? So, well, maybe I can say, like a brilliant student from the geoinformatics group had this clever idea, or original idea. Let's also incorporate the nearest observation, the second nearest, the third nearest, and the distance to that as additional explanatory variables in machine learning. So that is really behind the idea of random forest spatial interpolation. And so that is a paper that came out only 2 years ago. Alexander came up with the idea, but you see you see the names of people from the geoinformatics group. And I don't want here to promote my own work, but okay, so I'm also a co-author of that paper. And the idea of random forest spatial interpolation is that, well, as usual, when you do machine learning, you have your target variable. You need, of course, always measurements of your dependent variable. You do overlay with the covariates, the environmental, the remote sensing kind of covariates, and you get your covariate. But you do, in addition, you also look where is the nearest observation and how far is it away from the prediction location, both for the calibration data as well as for your prediction locations. And you add those nearest observations and the distances as additional explanatory variables to your machine learning algorithm, and you fit your model in the usual way and you get your predictions. Now, random forest spatial interpolation can indeed outperform just a standard machine learning random forest algorithm, but it's not like it's suddenly like 100% better or so. They are usually only small improvements. Here you see, for example, random forest spatial interpolation, let's only look at this one over here, it has a higher amount of variance explained, R square, a higher concordance correlation coefficient, I don't know, it's some kind of a correlation coefficient. It has a smaller mean absolute error and a smaller root mean squared error than all the other techniques here. This is 1.4 is lower than all the others. But actually quite interesting is that inverse distance weighted interpolation, that basic from the old times spatial interpolation was actually in this, well, it's only one specific case study, of course, was actually not so bad after all. It, for example, did better than space-time regression kriging, as you can see. So it's not always easy to predict beforehand what is the best technique. And what I like most really about random forest spatial interpolation, it's like completing the circle. We are back to where we started. We're starting to use again those measurements at nearby locations, the first law of geography when we predict. But of course we do it in a much more advanced way because we also take into account the external environmental explanatory variables, and we have a much more flexible model to predict, to calibrate. Okay, so I am getting to the end of my talk. I hope time-wise I'm okay. Yeah. So I think spatial interpolation, my goal was to give you like a bit of an overview of the history of spatial interpolation, starting from the 1970s to now. And it has come a long way, the same as with the concrete. And it started with simple deterministic models, but now it went to, well, geostatistics, the kriging, and also the machine learning. And the Belgrade geomathematics group has really made substantial contributions to the kriging, regression kriging, and machine learning. But I think their work is not over. I hope they don't mind. It's maybe a good message. You still have some work to do. And let me show you some of the topics that I would like them to work on in the coming years. Well, maybe there is a possibility to refine machine learning. Many of those techniques are actually already quite advanced, but there is a room for improvement. For example, deep learning and convolutional neural networks. Convolutional neural networks really take into account the structure, the spatial structure of the environmental explanatory variables. So it's not only the variables at that location that you use, but also the neighborhood information. So that might be in some applications actually very worthwhile to explore, but they are computationally very demanding and they also have high data requirements. Machine learning is of course a very broad topic, and for example they also use it, I think this is a typical example, to predict from a picture, is this a dog or is this a cat? And so if you train the model with many pictures, it's able to predict pretty well whether the picture is from a dog or a cat. And the convolutional neural networks, they take this texture, the local texture into account, and they can improve. So maybe it's also something useful in the earth and environmental sciences. And we are already exploring that, but I think the geoinformatics group might contribute to that. A problem with machine learning is that you want to avoid extrapolation in feature space. And okay, this is again some jargon, but the feature space is basically the space of your environmental covariates. You can imagine, for example, if you train your model with elevation data from measurements where the elevation is, let's say, between 100 and 500 meter, but then you apply your model to predict at a location where the elevation is 1,000 meter high or 2,000, you're extrapolating beyond the range of measurements used for calibration, and then you're in trouble, like we used to be also when we do linear regression in statistics. So you want to avoid that. How can we deal with that problem, avoiding extrapolation in feature space? And one way of avoiding that is, of course, to come up with clever sampling designs that can avoid that. When we do spatial interpolation, we need measurements. Whether we use inverse distance or kriging or machine learning, we need to train our model with measurements, and we usually ignore the fact that those measurements have errors. There are measurements, especially like in soil science, you take your soil sample, you measure the arsenic or you measure the organic carbon content, but that is only a measurement. If you would repeat the measurement, you probably would get a different number. So you'd like to include the errors in your measurements when you calibrate your machine learning model. And there's really a lot of work still to be done in that area. I didn't really explain cross-validation, but it's a way of, checking how well did I do. And we have developed quite some techniques for cross-validation. The idea is to put aside part of the measurements, use the other data to predict at those, put aside measurement locations, and repeat that for all the locations, and then you can compute your root mean square error. But if you use standard cross-validation, you're in trouble when your data is spatially clustered, because the outcome of that analysis will be dominated by the sub-areas where you have a high sampling density, where you tend to do better. So we want to, correct for that mistake, and some people have developed what they call spatial cross-validation, but I think spatial cross-validation is not the right answer. It has to be done in a different way. So that's a challenge also, and I also hope for the geoinformatics group to work on. Another thing is, and I'm coming to an end, that spatial correlation as what we use in geostatistics, it's not really incorporated in machine learning. Random forest spatial interpolation in a way does that, but it doesn't make use of a semi-variogram of spatial correlation. So maybe that could be included in machine. That's really a challenge to do that, but actually, it would be necessary. I also didn't really mention uncertainty quantification. So if you're interested in that, because when you do spatial interpolation, you make spatial interpolation errors. You like to know how big are they. Well, actually, the kriging and some specific machine learning algorithms can quantify the prediction error. And it is in the chapter that is in your book. So if you are interested, you can check that. But that is always predicting at points when we do in spatial interpolation. And sometimes we're not interested in the values at points, we want averages. And that really influences the uncertainty quite a lot. And in order to really properly quantify that, you need to take into account the spatial correlation. I think the geoinformatics group of Belgrade University is also really, really strong in geocomputation and having the right infrastructure, the machinery, the software, the hardware, and really to deal with the computational load of these techniques. And so that is, of course, needs continuous development. And something that wasn't mentioned so far, I mean, we're talking here about research, but of course, education is very important too. You're a faculty of civil engineering, you teach your students, and so it's very important that we educate the next generation of geoscientists with these techniques so that they are skilled and they have the expertise to apply those techniques after they graduate. And actually, it was only this weekend that I learned that the faculty has started a new program on geoinformatics this year, or maybe last year, I'm not sure, but fairly recently. So I can see that you are working on that. So that is really pleasing to hear. Okay, thank you for your attention.
Thank you, Professor Heuveling, for this presentation, and especially for giving us a look behind the curtain, because we are end users of geospatial data. We use them every day, actually. But now we heard that the quality of this data actually depends on this interpolation, right?
Yeah, that's right, yeah.
Okay, so we have enough time for at least one question from the audience. Yes, please.
Gerard, thank you for a very nice talk and presentation. I would like just to ask a question you mentioned on the end related to the quantification of uncertainty. So what do you think, is it going to be possible to include something like we have with quantile regression forest, but do do you think it is going to be possible to have something similar with deep learning techniques?
Okay, yeah. Yeah, that's a good question. And so in my presentation, I didn't really say very much about quantification of uncertainty. And I did mention at the end, like you're saying, that there are ways of quantifying the prediction uncertainty at each and every prediction location in machine learning. The quantile regression forest is an example of that. But not all interpolation, machine learning techniques can do that. So, and I actually don't know about artificial neural networks, whether it's able to do that. I think I read a publication that they do that, but so I think we have to look for the literature a bit more carefully, closely. It is, you know, in quantile regression forest, it's basically you use the existing random forest algorithm, but you just replace the measurements with you know, the binary, whether you're above or below the quantile of interest, a certain threshold. So maybe it's possible to do the same with neural networks, but I cannot answer you right now.
Thank you.
We have another question.
I'm not really in this field, but as you mentioned, that the sampling of data is very important. So I heard that you spoke about Voronoi polygons, and I know that some colleagues are trying to, let's say, optimize the positions of sensors to get the most covered space by using these Voronoi algorithms to get the least inscribed circles, the least diameter inscribed circles. And as I see, this is a multidisciplinary approach. So was in these, let's say, in past, some algorithms used for, let's say, choosing the places where the data are taken? Not only in these modern techniques, but in the past, in, let's say, building stations for measuring the data. Was it used already? Or it is, the measurements are just taken from the stations?
Well, thank you for this very interesting question about, this is really about spatial sampling designs. And we often, for example, you know, the optimal spatial sampling design depends on your goal and also depends, for example, in this situation, on the spatial interpolation technique that you are using. So if you want to use nearest neighbor interpolation, maybe you indeed want to have like a regular distribution of your points so that those Voronoi diagrams, those Voronoi polygons are more or less equal size everywhere. But if you, for example, use geostatistics, then it's usually not a good thing to sample your points in a regular design, because part of the Kriging, the geostatistics, is you need to quantify the spatial correlation as a function of the distance. You need the semi-variogram. And that means you also need to know the short distance spatial variation, because it's very essential that you know it to optimize your interpolation. So then you need to make sure you also have some clusters of observations so that you can estimate the semi-variogram. If you use machine learning, you have to avoid extrapolating in feature space. So then also you not only should look at the geographic space, but you also have to take into account, for example, in one of my courses, I let my students interpolate precipitation in Turkey. I worked with a PhD student from Ankara University, and she shared with me the data from the meteorological stations in Turkey. I think there's about 250 stations spread over Turkey, and then we use regression Kriging, for example, to interpolate the annual rainfall. But those stations, which of course is not so strange, they are not at the highest points of the mountains in Turkey. So if you use elevation, because we know that elevation is correlated with precipitation, if you use elevation as an explanatory variable in regression Kriging, and your training data are from elevations from 0 to 1,000 meters, but you predict the top of the mountain, 2,500 meters, you're extrapolating in the feature space. So definitely, maybe answering your question, many of the spatial data sets that we use for spatial interpolation, they are what we call legacy data sets. We had no influence on the design. So if we, as geoinformation scientists or spatial interpolation experts, would give advice, then we would probably come up with different designs that are used. Also, those meteorological stations in Turkey, they are never close to one another, which makes sense to me, because if you put a station somewhere, you don't want to have the next station only 10 or 20 kilometers away from it. But actually, for geostatistics, you need it. So in projects where, you know, it may make sense, and it's not, by the way, it's not only about where do you sample, but it's also about how many. So can you afford 1,000 observations or 500 when you have to do a spatial interpolation? The more, the better, but it will also be more costly. So it's like a trade-off between the accuracy of your map and the cost of investment. And I think that we still have quite a lot of work to convince the end users, the clients, that they should pay attention to these issues about spatial sampling design optimization, because they influence the quality of the final map. So in practice, often we work with data that are maybe not really optimal for the goal of spatial mapping. Is that answering your question sufficiently?
Yes, yes.
Okay.
Thank you for these extensive answers. So by this, I think that we are finished with this first conference session. Now it's, yeah, thank you, Prof.